Low-tech magazine, direct solar power, off-grid without batteries. Using solar panels without backup infrastructure makes renewable energy production much more affordable, efficient, and sustainable. August 25th, 2023. Written by Krista Decker. Translations available in French, Dutch, Spanish, Italian. Conventional solar installations do not question our dependence on fossil fuels and the energy-guzzling lifestyle that results. Both rooftop solar panels and large-scale solar farms provide us with all the power we want, even when the sun is not shining. That is because these systems use the central grid, which largely runs on fossil fuels, as a kind of battery to cope with power shortages. Although grid-connected solar panels can reduce the fossil fuel consumption of thermal power plants, these savings are at least partly offset by the additional fossil fuels required to build and maintain what is essentially a dual energy infrastructure. Combining solar and wind power can further increase the share of renewable energy in the power grid, but this requires further infrastructure development. Apart from energy, this also demands a lot of money and time. Replacing fossil fuel-fired power plants with energy storage so that surplus electricity generated on sunny days can be stored for when there is no or insufficient sun encounters the same problem. Energy storage, whether integrated into a power grid or located at individual households off-grid systems, is very expensive and carbon-intensive to build and maintain. Autonomous solar installation. The production of solar panels obviously costs money and energy. However, the financial and energy costs of the associated backup infrastructure are many times higher. For grid-connected solar installations, these costs are very difficult to calculate precisely, but for autonomous solar installations, without grid connection and with their own energy storage, it is a lot easier. As an example, I will therefore take the small autonomous solar installation that powers my living room in Barcelona. This system consists of two 50-watt solar panels on the balcony, a 100 amp-hour lead-acid battery, and a 10 amp charge controller. The energy generated is used for lighting, the music system, and charging laptops and other electronic devices, among other things. The initial financial investment was €340, 120 euros for the solar panels, 170 euros for the battery, and 50 euros for the charge controller. But while the solar panels should last 30 years and the charge controller about 10 years, I have to replace the lead battery on average every 3 to 5 years. Over a 30-year lifespan, the costs then amount to 120 euros for the solar panels, 150 euros for the charge controllers, and, in the best-case scenario, 1,020 euros for the batteries. The batteries and associated charge controllers therefore account for about 90% of the total lifetime costs. Energy storage also dominates the plant's embedded energy in resulting carbon emissions. Producing my lead-acid battery took 1,200 megajoules, MJ, of energy. Over a 30-year lifetime, 6 batteries at best, that equates to 7,200 megajoules. The 3 charge controllers add another 360 megajoules over a 30-year lifetime, bringing the total energy consumption for the battery system to 7,560 megajoules. In contrast, the production of solar panels only costs 2,275 megajoules out of a total of 9,835 megajoules. Conclusion: more than 75% of total fossil energy consumption is due to energy storage. Other types of batteries would not significantly change this conclusion. For a comparable off-grid system with lithium-ion batteries, the energy storage would account for about 95% of the total lifetime cost, which is almost double that of a system with lead-acid batteries. Assuming an optimistic lifetime, 10 years, and including charge controllers, lithium energy storage accounts for some 70% of the energy invested in a solar grid system. For nickel-iron batteries, the energy storage would account for 85% of the total lifetime cost. There are no energy cost data. The scale and location of the solar installation also make no difference. A larger system needs more solar panels, but also larger batteries and more expensive and powerful charge controllers. The ratios remain the same. The only factor that may give the solar panels a slightly larger share of the total cost is the structures on which they are mounted. I don't take this into account because I built them myself from waste wood. However, if the solar panels are mounted on a roof, a DIY solution is less obvious. But even in that case, the cost of energy storage remains by far the biggest consideration. Direct solar energy, much cheaper and more sustainable. Unlike fossil fuels, the sun and wind are not available on demand. The problem with our approach to renewable energy is that we insist that power should always be infinitely available, regardless of the weather, seasons, or time of day. Matching energy demand to supply, as was done in the past, would lead to dramatic reductions in the cost and use of fossil fuels. For example, if I omitted the battery storage of my solar installation, my system would become about 10 times cheaper, 120 euros instead of 1,290 euros over a 30-year lifetime. Alternatively, I could spend 1,290 euros on solar panels alone, which would give me a solar system of 1,075 watts. That's 10 times the capacity of the setup with batteries, more than what would fit on the balcony. Without the battery and charge controller, the energy cost of the installation also drops from 9,835 megajoules to 2,275 megajoules. In other words, I could generate at least 4 times as much solar energy with the same investment in fossil fuels. How can direct solar power be practical? All well and good, but the sun does not shine after sunset, and the amount of solar energy varies throughout the day and year. So how then can using solar panels without batteries, or other backup infrastructure in the case of grid-connected installations, be practical? To answer the question, we look at a pioneer of direct solar power, the Living Energy Farm. This environmental education community in the U.S. state of Virginia is completely off the grid thanks to solar power, but only 10% of the solar power generated passes through a nickel-iron battery. However, the solar panels provide power for several homes, a communal kitchen, a metal workshop, and a farm. The solar installation has been in operation since 2011 and consists of separate systems with a total peak power of 1,400 watts. In comparison, the average peak power of a residential solar installation in the UK and the US for one household is 4,000 watts and 6,500 watts, respectively. As in my flat, the Living Energy Farm uses energy sparingly, but the fact that hardly any batteries are used has other reasons. Some appliances are only used during the day. A first reason is obvious. Some electrical appliances and machines are only used during the day. This is true, for example, of all machines in the metal workshop, including a bandsaw, compressor, grinder, circular saw, lathe, milling machine, and drilling machine. It also applies to agricultural machinery such as a grain mill and a deep well pump. Linked directly to solar panels, these machines offer all the capabilities of modern grid-powered technology, with the exception that they can only be used during the day. On a much smaller scale, I have used direct solar power for a soldering iron, glue gun, and irrigation pump for the balcony at home. Other examples of appliances and machines that could be used only during the day include hoovers, sewing machines, washing machines, game consoles, laser cutters, and 3D printers. It is not so difficult to imagine a modern society where activities such as vacuuming and DIY chores only take place during the day. It is certainly not a return to the Middle Ages. Moreover, not all electrical appliances require constant attention. Washing machines or dishwashers that trigger automatically when the sun shines are often cited example applications of a smart power grid. But that approach relies on an extensive infrastructure of electricity transmission, communication networks, and electronics-packed appliances. In contrast, in a decentralized direct solar approach, the intelligence is provided by the sun and the rotation of the planet. A direct solar-powered washing machine or dishwasher can be fully charged and switched on in the evening. The machine then starts up automatically in the morning. You can even use timers, electronic or mechanical, to run different appliances one after the other. Whether clouds pose an additional limit to direct solar installation and to what extent depends on the size of the solar panels. Doubling the area of solar panels guarantees sufficient solar power during moderate cloud cover, while the installation remains much cheaper and more sustainable than a system with batteries or other backup infrastructure. An even larger area of solar panels could provide sufficient energy during heavy cloud cover, but increasing the size of the system tenfold brings the cost back to the level of an autonomous system with batteries. Quadrupling the area makes the system equally dependent on fossil fuels again. Many appliances already have batteries. Direct solar power does not rule out the use of electrical appliances after sunset either. As mentioned, the Living Energy Farm has a modest battery system, providing power for lights, fans, and electronic devices after sunset, among other things. In addition, many modern appliances already have built-in energy storage. This is the case for all kinds of electric vehicles, for most electronic gadgets, and for older electrical appliances with AA batteries. Consequently, these types of devices can be charged with direct solar energy during the day and then used for several hours after sunset thanks to the built-in battery. Combined with a lithium-ion power bank, a direct solar panel can also make it possible to charge USB devices after sunset. This strategy can even work for lighting, as there are many battery-powered lamps that you can use as modern torches hung in different parts of rooms and buildings. Of course, outsourcing chemical energy storage to the device is not the most sustainable option. The production of lithium-ion batteries requires fossil fuels, and, unlike lead-acid batteries, they are not recycled. The best solution, of course, is to reduce the use of electrical devices, but charging them with direct solar energy is a lot more sustainable and efficient than other batteries or a fossil-fueled electricity grid. If we only use high-tech devices, then preferably in the smartest way possible. If we use high-tech devices, then preferably in the smartest way possible. Non-electric energy storage. A third reason why direct solar power is more practical than it initially seems is that some electrical appliances can be used after sunset thanks to thermal energy storage. This is much cheaper and more sustainable than electrical energy storage. Thermal energy storage is already fairly well established for space and water heating systems, which store solar heated water in an insulated boiler or, for space heating only, in the building envelope. It is no surprise that the Living Energy Farm has such systems, and solar thermal energy also provides hot water in my flat. However, the same approach also works for two important household appliances that need to work after sunset and also consume a lot of electricity: the fridge and the cooker. Instead of storing electricity from a solar panel in a battery to then power a fridge or cooker after sunset, these appliances on the Living Energy Farm use thermal insulation. This keeps the heat inside, in the case of the cooker, or outside, in the case of the fridge, when there is no power supply. The thermal insulation also ensures very high energy efficiency, which means that each of these appliances can operate on a solar panel of just 100 to 200 watts. A direct solar-powered fridge. It is perfectly possible to connect a conventional fridge or freezer directly to a solar panel, but such an appliance would heat up very quickly at night. Even refrigerators with the most energy-efficient labels have a relatively limited insulation thickness, usually 2.5 centimeters. However, if that insulation thickness is increased to about 12.5 centimeters, the energy consumption of a refrigerator drops by a factor of 4. The passive cooling capacity of a refrigerator can be further increased by adding thermal mass in the form of a water tank inside the appliance. During the day, the solar panel cools the water or converts it to ice. At night, this cold water or ice slows down the heating of the refrigerator. A direct solar-powered fridge also opens at the top, not at the front. Cold air is heavy, and so much less energy is lost that way when someone opens the door. All these design choices add up to a spectacular energy efficiency. A study of direct solar refrigerators in very sunny regions, Texas and New Mexico, in the USA, showed that they maintained their cooling capacity for 6 or 7 days without power supply. The units operated year-round with solar panels of only 80 watts to 120 watts. The Living Energy Farm powers its solar refrigerator with a 200-watt panel. Unlike solar heating, solar cooling is optimally tuned to seasonal variations in solar radiation. Cooling requires more energy in summer when there is more solar energy. The aforementioned refrigerator in New Mexico recorded electricity consumption of 406 watt-hours per day in the summer and only 230 watt-hours in the winter. Moreover, the technology can be used throughout the cold chain, of which the household refrigerator is only a small but essential part. Another application is air cooling, although this is less well researched and more challenging. A direct solar electric cooker. In principle, a conventional cooker can also be connected directly to a solar panel, but as with the conventional fridge, it is not very practical. You can only cook during the day, and you have to install a lot of solar panels. A single hot plate needs 1,000 watts of electrical power. A solar electric cooker solves these problems by packing the cooktop with thermal insulation. The technology is basically a combination of an electric cooktop and a hay box. Thanks to thermal insulation, an electric solar cooker slowly accumulates heat during the day, which can then be used for cooking after sunset. In this way, a much lower power supply can be sufficient to achieve high temperatures. Think of it as charging your cooker, not with electricity, but with heat. Researchers at the U.S. California Polytechnic State University, Cal Poly, built the first solar electric cooker in 2015. Their 12-volt device, which has since been further developed, needs only a 100-watt solar panel to work. It boils a liter of water in an hour. With a full day of sunlight, it can cook almost 5 kilograms of beans, rice, stew, or potatoes. Cooking after sunset is possible by using a cooking pot with a much thicker bottom, 5 to 10 kilograms. Cal Poly's research team managed to bring the temperature of that solid heat storage to 250 degrees Celsius in 5 hours with a 100-watt solar panel. They were then able to boil a liter of water in 3 seconds after sunset. In another test, they stir-fried 1 kilogram of vegetables in 2 minutes. The ideal configuration consists of 2 cooking pots, one with and one without heat storage. Thus, an electric solar cooker can cook both slowly and quickly, depending on the time of day and the dish. Thermal or electric. Like solar water in space heating systems, cooking and cooling can work both with and without electricity, with photovoltaic panels on the one hand and solar thermal collectors on the other. But while solar space and water heating are more cost and energy efficient without electricity, for solar cooling and solar cooking, it is just the opposite. Space and water heating require relatively small temperature differences, which can be provided by low-cost solar thermal collectors made of glass plates and water pipes. In contrast, cooling and cooking require larger temperature differences, which require more sophisticated vacuum tube or parabolic solar collectors, and these are more expensive than photovoltaic panels. The only exception is a simple solar cooker, an insulated box with a glass top, but it cannot achieve such high temperatures. Moreover, an electric solar cooker has some additional advantages. With a non-electric appliance, you have to cook outside, which is less practical but also less efficient, especially in winter. A thermal solar cooker will lose more heat to the environment. An electric solar cooker is also more energy efficient because it is insulated on all sides. It also works better in cloudy weather and can be used after sunset. At the Living Energy Farm, the parabolic solar cooker is only used in optimal conditions, at full sun and high outdoor temperatures. What are the technical challenges? Although the Living Energy Farm is putting all these applications of direct solar energy into practice, there are some technical challenges for those who want to follow suit. Almost all our modern technology is designed to operate with a stable and uninterrupted power supply. It doesn't have to be that way, but for now, direct solar panel usually requires some tinkering. A direct solar system is much easier to build than an autonomous system with batteries, but it often requires modifications on the appliance side. Some devices can be connected directly to a solar panel. It is enough to connect the positive and negative contacts of the solar panel and the device. For example, machines with a DC motor tolerate large fluctuations in the power supply. The metal workshop and agricultural machinery at the Living Energy Farm worked this way. If clouds block the sun, the combined electrical load can become greater than the power supply from the solar panels, but this does not stop the machines. All of the engines will slow down because they share the available energy, but they all continue to do useful work. The same applies to all appliances that work on the basis of resistive heating elements, such as kettles, hot plates, or electric heating systems. They work regardless of power or voltage, just slower or faster. A direct solar-powered fridge preferably operates on a variable DC compressor, which can adjust its speed according to the varying solar power production. Many other devices need a specific and stable voltage input, which usually does not match what the solar panel produces. This can be solved by placing a DC-DC converter, a buck or boost converter, between the solar panel and the device. This is a small electronic module that converts the fluctuating voltage of a solar panel into a constant output voltage for a low voltage device, 5 volts, 12 volts, or higher. If you use an inverter in addition to this, even mains appliances can operate directly on a solar panel. DC-DC converters are essential for all appliances that contain electronic components. This is the case for many appliances today, including those such as washing machines or coffee machines, that until recently operated without electronics. That often gives you two options to run such appliances on direct solar power. You can either fit a DC-DC converter or modify the appliance by bypassing the electronics. DIY manuals in commercial devices. Most direct solar power applications operate at low voltage, so you can safely do it yourself. Low-Tech magazine will soon publish a manual on this. However, the Living Energy Farm uses direct current with higher voltages for a number of applications. Examples are the machine tools in the metal workshop, 90 volts, and a number of powerful electric solar cookers, 48 volts and 180 volts. It is not a good idea to build these systems yourself unless you have the help of a qualified electrician, as these voltages can lead to fatal accidents. Those wishing to build their own low-voltage electric solar cookers will find comprehensive manuals at both Living Energy Farm and Cal Poly. The devices can be made with simple materials. The insulation material should be fireproof. Example materials are rock wool, fiberglass, natural wool, or clay goed. Different technologies can be used for heating elements, but embedding nichrome wires in cement is the simplest option. These wires can be taken from a variety of appliances such as toasters, ovens, and hot plates. In principle, the heating wires can be attached directly to the cooking pot, but it is more practical to make a heated nest in which a pot can be placed. Does direct solar power waste energy? The sustainability of a solar installation depends not only on the energy required to produce and maintain the infrastructure, but also on the energy produced by the solar panels during their lifetime. Some people will argue that direct use of solar power is inferior to conventional grid-connected or battery-powered solar installations in this respect. After all, The Hoover, washing machine, and power drill are not used every day, and if no electrical appliance is connected, then a solar panel will not produce power either. Consequently, the amount of electricity produced by the panel will decrease over its lifetime, while the energy needed to manufacture the panel remains the same. This makes the power from a direct solar panel more carbon intensive. However, because energy storage in batteries or the grid-connected alternative accounts for such a large proportion of the total energy invested, a standalone solar panel can waste quite a lot of energy before it becomes less sustainable than its counterpart with battery storage or grid connection. Moreover, direct use of solar power avoids the charging and discharging losses caused by batteries, or the energy losses in the transmission of infrastructure for grid-connected systems. Both have to be offset by additional solar panels. Furthermore, solar panels connected to batteries or the grid also waste power, a consequence of the large difference in energy production between summer and winter. Maximizing direct solar power with collective services. Nevertheless, it is important to maximize the energy production of a solar panel. In that context, it is useful to return for a moment to the original example system located on my balcony. Direct solar power could be a nice addition to the system, especially for the fridge and cooker. It was because of these appliances that I concluded in 2006 that it was impossible to completely disconnect my flat from the grid. However, the Living Energy Farm shows that it could be done. There is room for a further 200 watts of solar panels, 4 times 50 watts, on the balcony, enough to power both a thermally insulated fridge and hob. Additional battery capacity would not be needed. For other appliances, however, direct solar power is of little use in my case. It would not be very efficient to install an extra solar panel for the washing machine or the power drill, as they are only used occasionally. This seems to play into the hands of a smart electricity grid, because that way many households can use the same solar power. There is always someone who needs to wash clothes or drill a hole. However, such a smart grid does require a lot of infrastructure, even if direct solar power were to be used at that scale. It may not require batteries or fossil fuels as backup, but it does require transmission and communication infrastructure. The Living Energy Farm demonstrates an alternative solution: the communal organization of household tasks and work. Instead of a communal power grid distributing energy to many individual households, we can set up collective services with decentralized energy production. In Living Energy Farm Communal Workshop, direct solar power can be used much more efficiently than in an individual workshop that is only used occasionally. A collective laundry in each street would also use direct solar power much more efficiently. Moreover, we save a lot of energy on building appliances this way and gain a lot of space. Direct wind power? This strategy becomes even more important if we choose not direct solar power, but direct wind power, or a combination of both. The Living Energy Farm is located in a sunny region, but the same approach could also work in windy places. However, there is an important difference between solar power and wind power. The efficiency of a solar panel does not depend on its size, which makes solar power ideal for decentralized energy production. In contrast, the efficiency of a wind turbine increases more than proportionally as the rotor diameter increases. Much better than one turbine per household, therefore, is a somewhat larger wind turbine for a community of households, e.g., for powering a collective laundry or workshop. Subscribe to our newsletter, support Low-Tech Magazine via PayPal or Patreon, read Low-Tech Magazine offline.